Welcome to another session of CHE2511 Basic Organic Chemistry with me Jackson, and today we continue and extend our discussion on Newman projections. Just another way of representing conformers to show how the sigma bond between two carbon is rotated. Imagine you've got a compound and then you're told to cite between let's say C2 and C3 of the carbon. It's like this is your front carbon and this is your back carbon, or this is your front carbon, this is your front carbon, this is your back carbon. Depends. But I like making this as my front carbon and this as my back carbon. So how are we going to do it? How do we write Newman projections? If you're told to cite between two carbon, let's say C2, C3, it means you write one at the front. When you're writing Newman projections as such a way that if I write, for example, this is usually the front carbon, this is usually the front carbon, and then this, the circle is usually the back carbon. So it's like you're viewing it, you're only able to see the front carbon, and then you're not seeing the back carbon. You're able to see the front carbon, you're not able to see the back carbon. It's at the back. So it's like you're, for example, it's like you're facing your screen, and then your screen, the screen that you're looking at, is the front carbon, and then the back of your phone or your laptop is the carbon number 2. You're not able to see it, it's eclipsed. So that's how our Newman projection are. And when you write something like this, this is your front carbon, and this is your back carbon. So your front carbon with its 3 groups, and the back carbon with its 3 groups. So let's use this example that we've been given, this question as an example. For example, you are viewing through, you're carefully considering 3-ethylheptane. Heptane has 7 carbons, 1, 2, 3, 4, 5, 6, 7, and on carbon number 3 we have an ethyl. 1, 2, 3 with an ethyl group. So this is carbon number 3 and this is carbon number 4. So you are viewing down C3 and C4 bond. So this is the bond that is rotating here. It's the bond that is rotating. So you're told to draw Newman projection formulas for each of the eclipsed and staggered conformation resulting from the rotation about C3, C4 bond, and clearly label each of the conformation with a letter. So how are we going to do it? So if you're told to look between 3 and 4, I like making my 3 as the front carbon and my 4 as my back carbon. Remember, this is the back carbon. So when I come on 3, carbon number 3, the 3 groups, you're not considering this bond between 3 and 4, which is being rotated. It's the one that is rotated, so you're not considering this bond. So the 3 atoms that are attached, or the 3 groups that are attached to this carbon 3 here, we have got this group here and this group here, and we've got a hydrogen that we can see. So I can put my hydrogen here. So this is my what? My front carbon, and then this is an ethyl group, CH2, CH3, and here we have CH2, CH3. And then when you look at the carbon at the back, which is carbon number 4, so again not considering this bond, we're looking at this carbon, the 3 groups that are attached. There's a hydrogen here, and this will 1, 2, 3 propyl group. So again you do the same. Here, this is the carbon at the back. So we've got 2 hydrogens and the propyl group, which is CH2, pardon my drawing, CH3. This is a Newman projection formula, and I like maintaining my front part. Usually most textbooks you find that they're rotating this part, and by rotating it means these groups this group here comes here, and this group comes here. This group comes here. That's a rotating. So for you rotate once, this group comes here, meaning this will be here and this will be here. That's rotating one. But I like maintaining this front structure. So meaning that if I've drawn my H here and my other H here, for example, and another group here, I like maintaining this structure. I love rotating the groups at the back. This, and this. So A, B, C. So this will be like my backbone. I won't be rotating anything, the front carbon. And then I'll be rotating. In another rotation, A comes with this B. In another rotation, B comes with this C. In another rotation, C comes with this A. So that's how I like to do it. Because you might end up drawing the same structures if at this point you at one point you draw you rotate on the front carbon, at the other point you rotate at the back carbon. So it's like choose which one you're rotating, choose which carbon of that sigma bond you're rotating. So I wrapped out my structure, but it's just the same. 1, 2, 3, 4, 5, 6, 7, and carbon number 3. Got this. So this is 3 and this is 4. So if you're told to draw the eclipse form, so I like maintaining my backbone, like I said. So this carbon number 3, we had drawn something like there's a hydrogen, and then we got 2 methyl groups, ethyl groups. And then the back carbon, carbon number 4 has hydrogen, so this hydrogen, and this propyl group are the ones that I'll be rotating, the one at the back. This comes here, so this is a gauge because the angle between this front carbon, remember this hydrogen is on this front carbon, and this hydrogen is on this back carbon, so the angle here is 60 degrees. So that's like what we call a staggered. The angle is 60 degrees. This is 60, this is 60. Remember this group is at the back, this group is at the front, back, front. So the angle is 60 degrees. That's eclipsed, that's staggered. And for eclipse, so to draw other staggered conformations, you just remember I said hydrogen, this group and this group, I'm maintaining them. So the other structure, this group will come here, and the other structure, this same group will be here. So that means you would have rotated. So you can draw 1, 2, 3, 3 staggered conformations for this guy. Then for eclipse, you're eclipsing the bond. Again, I'm maintaining the backbone, the front carbon here, CH2, CH3. Again here, CH2, CH3. And then eclipsed, it means the groups at the carbon number 4, which is at the back, which is a hydrogen, and this propyl group, they're eclipsed in such a way that they're behind. For example, the hydrogen is behind here, and the other hydrogen is behind this group, and this isopropyl group, these are actually methyl groups, and the isopropyl group is also here, eclipsed. So this is an eclipse conformation. Again, for the eclipse, you maintain H, this and this. The front carbon don't move anything, but in your next structure, this draw it here, and again this draw it here. So you would have had your 1, 2, 3 eclipsed conformation, but then you see like 2 of them are similar because the groups. Yeah. So when you do this, you would have drawn your eclipse conformation because these are aligning in such a way that the dihedral angle is 0. between the front carbon and the back carbon, the group. It's like you're viewing from the front. This is the front carbon. You're not able to see the back carbon. Yeah. So in terms of relative energies, which is question B, I'll make another video because I don't want this video to be long enough for it to get boring. So this is basically how you do Newman projection. You can try for other structures, but you consider the bond that you are viewing to. For example, if you're given butane, we'll draw for another compound so that it gets clear. So you turn to butane, and the total site between C2 to C3. You do the same. You write the front carbon. I like making my 2 as my front carbon. C2. And you see what groups are on C2 here. It's hydrogen, hydrogen, and this methyl group. So hydrogen, you can put it wherever you want, and then the methyl group. So this, I won't change it. I want to rotating the groups on the back carbon, which are carbon 3, which is again hydrogen, hydrogen, and a methyl. So hydrogen, hydrogen, and the methyl. And the methyl group. So the next structure, this methyl will be here. Again, the next structure, this methyl will be here. But then if the methyl is here or here, it's the same structure. So you cannot draw that 2 for this one, the conformation, and the eclipse you just do like I did in the previous structure where the bonds are like this. So again, you're just rotating the back carbon. The atoms exchanging this atom with this comes here, this comes here, so that you don't get confused and write the same structure twice or thrice. Yeah. So that's what you do basically for Newman projection. In terms of gauge, so in the next video, discuss what a gauge is. This is just simply 60 degrees, but what is it? How is this bond here in the front and the bond, the group at the front and the group? What's the separation distance or the angle? 60 degrees is a gauge, but then if you compare this and you compare the biggest groups, the bulk groups, this and this, if you compare this is at the front, it's 180 degrees to this metal group at the back, and this is like 180 degrees because it's an anti-conformation. So we look at that in the next video, and in the next video I'll have all the conformation drawn out, or I have all the conformation drawn out to answer question B, because I will be able to tell which one is the least stable, which one is the most stable. Again, it's all about steric strain and torsional strain. If you don't know what these are, there's a video that I made on steric strain and torsional strain. I think that's question 1 of this tutorial session. So it's these two. Because of these two, they're able to tell this one is stable compared to this one. So staggered conformations are always stable compared to eclipsed conformations. Because you've got eclipsed, the groups are aligning together, so it's like they're close. And there's torsional strain, there's a lot of torsional strain and a lot of steric strain if at all the groups are bulky. And staggered, there's always 60 degrees, so at least the steric strain isn't much and there is no torsional strain. So in eclipse there's no torsional. In staggered there's no eclipsed. In staggered we don't have torsional strain. Torsional strain is for eclipse. So we'll discuss that in the next video when answering B.